Hello everyone, welcome back to the session. So in today's class we are going to learn about dipole. So basically what we're going to see is if you take a dipole and place it in an external electric field, what would happen? Okay, that's all we're going to cover in today's class. So before we begin, my name is Mohana. I'm a physics educator here at Unacademy. So I have my master's degree in physics. I'm also a plus verified educator here. And this is my Telegram channel link, so you can follow me using my Telegram channel, as well as if you see this is Unacademy ICSE and ISC board a common Telegram channel, so you can follow this channel as well. Okay, so with this note, let's begin. So just give me one moment please. Okay, right. Right. Okay. So first let's see what is an electric dipole. Okay. So electric dipole is extremely simple concept. Okay. So let's say you have a positive charge. So before that, let's say you have a positive charge. So if you have a positive charge, we know that it has field lines everywhere, but these field lines are going to be pointed radially outwards. Okay, and now let's say this is a negative charge. So obviously the negative charge is going to have field lines. In this case it will be pointed radially inwards. Now if in case you are taking a positive and a negative charge, okay, let's say you have a positive charge and a negative charge. Okay, so let's say the strength of this particular positive charge is somewhere around 2 microcoulombs. Okay, and let's say this is around -1 microcoulombs. Now for 2 microcoulomb, as an example, let's say this charge has around like around let's say around 5 or like 100 field lines. Okay, so for -1 coulombs, then this will have around 50 field lines, right? So what will happen, some of the field lines, when you bring these two charges somewhere, if you keep these two separated at a small distance, so about 50 charges from the positive charge would start and terminate at the negative charge. Okay, now electric dipole, when you see, what you have is basically two charges. Okay, you will have a positive charge, all right, and you will have a negative charge, and these two charges are going to be separated by a small distance. Okay, and the distance of separation between them, usually your textbooks takes it as 2a. That is, let's say this is the center O over here. Okay, then from here, from the center of the positive charge to this charge, this is going to be A, right? And from the center of this charge to here, this is going to be A again. So in total, if you see, the distance of separation between them is 2a. Okay, now if you look at the field lines, the field lines will always start at the positive charge and terminate at the negative charge. Okay, so if you have two charges, especially when these two charges, let's say this positive charge is around 2 microcoulombs, okay, and the negative charge would be -2 microcoulombs. So when compared to the previous case, what we are seeing here is the charges are equal, but they are opposite. One is positive, another is negative, but magnitude wise they are equal. So the number of field lines that a positive charge has, there would be an equal amount of field lines in the negative charge as well. Okay, and the field lines always starts at the positive charge and terminates towards the, it will always start at the positive charge and terminates towards the negative charge. Okay, so when you take two charges, equal and opposite charges, and if you're separating them by a small distance, okay, then it is called as an electric dipole, and the charges will begin at a positive charge and terminates at a negative charge. Okay, now electric dipole moment, it is a quantity which just measure the strength of the dipole. Alright, so if you have two charges, positive and negative over here, okay, whatever the negative charges, for example, if this is -5 microcoulombs, means this is nothing but +5 microcoulombs, right? So your dipole moment is given by this quantity P. Okay, and it is actually a vector quantity, so it has a direction. So the direction of the dipole moment is always from the negative towards the positive charge. So this is the direction of the dipole moment. Okay, so if you want to find what is the magnitude of the dipole moment, very simple. Take one of the magnitude of any one of the charge, because magnitude wise they are equal, right? And take the distance of separation between them. So let's say the distance of separation between them is 2a. Right, so this quantity is nothing but the product of one of the charge, magnitude of one of the charge, into the distance of separation between these two charges. This gives us an electric dipole moment. Okay, and it's a vector quantity, and its direction will always be from negative to positive. So if you have to write it as a vector equation, we know charge is positive, charge is a scalar, and over here a is nothing but it gives a position vector, so we can go as a vector. Now unit wise, very simple. Charge is given in terms of coulomb, and if you see the distance is given in terms of meter. So dipole moment is given by this formula, coulomb meter. Okay, so this is electric dipole moment. Now let's see, when you take this particular electric dipole and place it in an external electric field, so the dipole itself has a so if you see the dipole itself has an electric field lines. Okay, now you take such a dipole and place it in an external electric field line over here, and we want to know what happens. Now very simple, look at the electric field lines over here. Okay, for example, in this case the electric field lines, let's say we have two capacitor plates on two ends, and let's say you're connecting these capacitor plates to the to a battery. Okay, let's say it's positive and negative terminal of a battery. Then what would happen? So now this one side of the plate becomes positive and another is a negative, right? So this side of the plate is going to have positive charges. Similarly, this side is going to have negative charges. Now what will be the direction of the electric dipole moment in this case? It will always start in the positive charge and terminate at the negative charge, right? Because if you see field lines always for a positive charge, it begin at a positive charge and ends at the negative charge, right? So here it will start and it will start from the positive and end at the negative over here. Now in this particular field line, okay, now if you keep in this external field line, you're placing a dipole, electric dipole at an angle to this particular field. Okay, look at this angle that it's placed at, right? You're just placing it at an angle. Okay, let's say you're placing it at an angle theta. Now the distance between these two point charges, if you see, okay, these two electric dipole, these two charges, if you see, this distance is 2a. Okay, now obviously the dipole moment is always from negative to positive, right? And it will be in this direction over here. Now what we have is two charges, right? Now you place this dipole at an angle in this field. Now what would happen to this positive charge? So we can understand this by actually taking the, let's say this side, we said this is positive charge, and this side we have a plate which is negatively charged, right? So here we have a positive charge. What will happen to a charge placed in an electric field? Okay, very simple. This charge will basically a force would exert on this charge, which will attract it towards this negative plate. So there is a force exerted on this charge in this case over here, and the force exerted in this case, if you see, is in the direction, okay, is in this direction over here, right? So this is a positive charge, let's say this is plus q, and in this case there is a force exerting, but this is basically, this force exerted in this case, if you see, is nothing but equal to q into E, positive charge into E. How do we get this? Is very, very simple. Okay, we know what is electric field. Electric field is nothing but what is the force experienced per charge, right? So from this equation, if you see, what is force, which is nothing but charge times electric field. Okay, that's charge times electric fields, that gives you the force. Now if you see for this negative field, so this gives us the force equation, so this is for the positive charge, right? So what would happen towards this negative charge over here? Okay, around the negative charge over here, again this negative charge will be this will get attracted towards this positive side, right? It will tend to move towards this side. Now what will happen? So in this case, if you're writing the force equation in this case will be charge is minus q into the electric field E. Alright, so now look at what is the net force, okay, acting on this particular dipole. What is the net force acting? Okay, the total force acting on this particular dipole, that is force, the total force acting is because of the force exerted on the positive charge, that is plus QE, right? QE times the electric field, and the force exerted on the negative charge, that is minus Q into E, right? So this tends to be 0. So total force exerted on the dipole is 0, meaning total force in this case, total translatory force, right? In this case, the linear force, or the total translating force in this case, the net translating force on the dipole is basically 0. But if you see, there are two equal, okay, magnitude wise these two forces are equal, right? But there are two equal but opposite forces acting on the same dipole. Now on this, say you have learned it in your grade 11, on this in class 11, right? On the same object, if there is two forces acting in opposite direction, then it would basically constitute a couple, which would produce a turning effect or a torque, right? So because of that, this particular dipole tends to turn. Okay, so this particular dipole in this case, it will tend to turn, right? So if you see, if you keep this dipole at an angle, right, now it will tend to turn till it reaches a particular, till if you see, till it reaches, that is till if you see that there is a dipole moment, right, till the dipole moment becomes, the dipole moment is parallel to the electric field, till then it would basically turn. Alright, so if you see in this case, okay, we have the force times the distance, right? So from here what we can say, we want to find what is torque, right? Torque is nothing but either one of the force, okay, either one of the force times what is the perpendicular distance between them. Force equation we know, either any one of the force equation we know, it has actually been given by Q into E. This is the magnitude of force, right? We calculated what is the magnitude of force here, it's Q into E, right? But what is the magnitude of the distance? So in this case, if you see what is the distance between them, do not confuse and take the distance between the two two charges over here. You have to see, take the distance between the forces actually over here. At one force is acting in this direction, another in this direction. So you have to calculate this distance over here. Okay, now as this dipole turns, what we see the distance between these forces tend to reduce. Okay, and at one point if you see, there is they are totally equal and opposite. Okay, so here if you see, this distance we want to find. Alright, so if you want to find this particular distance over here, we can see this is almost as a right angle triangle, right? And this distance is basically QA. So let's do that here. We want to find this distance, right? So what are the quantities we know over here? We know this is a negative charge and this is a positive charge. We know the distance between them is basically 2a over here, right? And this is an angle theta over here. We want to find what is this distance, right? So if you want this distance over here, let's take this to be the this distance. Can we take, let's take this as d. Okay, so you want to find what is d. Okay, so d will be nothing but if you want this, you can then take sine theta. Okay, sine theta is opposite by hypotenuse, or in other word perpendicular by hypotenuse, because this over here is in the form of a right angle triangle. Alright, so from here if you take, here you get opposite or perpendicular, right? That is d divided by hypotenuse. This side is nothing but the distance between these two charges, that is nothing but 2a. So from here you can see d is nothing but 2 into a into sine theta. This is your distance d. Now going back to this equation over here, we have one of the force, right? One of the force magnitude is QE, and the perpendicular distance over here will become 2 into a into sine theta. Alright, so here we have one quantity, that is 2 into a, okay, into we have this quantity q, right? This is into e into sine theta. This quantity, that is basically what we have here, any one magnitude of one of the charge times the distance between them. This is nothing but, earlier we saw that this is nothing but dipole moment P. Okay, because since dipole moment is equal to Q into 2A. Alright, so this is P E sine theta. So this equation over here gives you what is the magnitude of the torque experienced, that is what is the turning effect that this particular when you keep a dipole at an angle in an external electric field, what is the turning, how much turning effect, that is the torque it experiences, right? That you can find using this torque equation. Now when we are talking about torque, we are talking about a turning force, right? So because we know this is force again is a vector quantity, right? So we can give this as a vector equation. So if you see, E is a vector quantity and P is, again, if you see, dipole moment is also a vector quantity, and there is one more quantity over here we see, that is sine theta. So from here we can actually know that this torque, okay, is nothing but in this case equal to P cross E, because you would have seen when you're doing cross product, sine theta comes for cross product. Okay, now there is obviously another question, why can't torque be E cross P? Okay, now this depends again on in which direction the vector is moving. Okay, so normally when you say the vector product, normally when you end up taking a vector product, okay, let's say these are two sides. Okay, let's say this is P vector and let's say this is E vector over here. Okay, because we saw that we have the electric field lines that are going straight, and in this electric field lines we have kept two charges where the dipole moment is placed at an angle, right? So there is an angle dependence over here. Now you can use the right hand screw rule to find which is the direction, or you can simply go by saying make sure the inner palm of your hand is facing towards the P vector, and if you see in this dipole which is moving, okay, this here you can notice that the dipole is rotating to adjust to the electric field, right? So it experiences a turning force till it becomes parallel to the electric field, right? So here the dipole is turning. So if you go from P to E vector, your thumb points downwards, because the thumb is pointing downwards, which means torque in this case will be given by this downward the downward vector over here. Okay, so in this case what we are saying, this particular charge finally when it comes parallel to the dipole moment, when it finally comes parallel to the electric field, there is no more torque produced. Why? Very simple. From the torque equation, again if you see the torque equation, tau is actually given by Pe sine theta, right? Now this is the direction of P vector, and look at the direction of the E vector over here. They are both parallel, which means angle between them is 0 degrees. Earlier case, see, this angle was more. As it turns, the angle tends to reduce and finally we get 0 degrees. Okay, so because of this, what we can say, the angle between them is 0. So what is sine 0? Sine 0, again, if you see Pe, and here if you write it as sine 0 is 0. So here this tends to be, here you tend to get torque to be 0. Okay, torque to be 0 means in this case, if you see, this is one of the special cases again. In this case, when the dipole is aligned with the dipole moment is aligned with the electric field, the two forces that is acting on the dipole moment are equal and they are acting opposite to each other, and angle dependence is, angle in this case is 0. Okay, angle the dipole makes with the electric field is 0. Okay, because of it, in this case the torque experience is 0. That is, in this case if you see, it is at a completely stable equilibrium position. Alright, now coming towards the coming towards the special cases. Now we want to see when would we see a maximum torque. Okay, so we know tau is actually equal to what? This angle tau is equal to P E sine theta, right? So in this case we are keeping this particular if you see the dipole perpendicular to this electric field. Okay, so this is the force experienced on the positive charge in this case, right? And this is the force experienced on the negative charge. Okay, so obviously the distance between them, and the dipole moment is always from negative to positive. So in this case, if you see this particular charge in this particular case, the dipole has to turn by an angle of about 90 degrees, right? Because this dipole is kept at an angle of about 90 degrees with the field. So the dipole is having an angle of 90 degrees with the field. Now obviously we know that sine, if you substitute for sine 90 over here, we know PE sine 90, sine 90 is actually 1, so we get PE into 1 over here, right? So torque in this case ends up becoming P into E. So here we end up getting maximum torque, because theta for 90 degrees you get the maximum angle. Okay, so this is again maximum torque. Alright, so this is one case where if you want to get maximum, when the dipole would produce a maximum torque, because it has to turn around by an angle of 90 degrees, then you would see that is angle is equal to 90 degrees, and you get torque is equal to P into E, that is just the dipole moment into the electric field. Okay, now very simple. Next special case, if you see the next special case we already saw, right? In this case, force acting, we know this is nothing but QE in this direction, and we know this is force acting is equal to minus QE in this direction. And now we just saw this case earlier. Torque in this case, dipole moment and electric field are parallel to each other. Okay, so in this case, look at the direction of the dipole moment, it's always from negative to positive. In this case, we have PE into angle between them, because they are parallel vectors, right? They are parallel to each other, angle between them is 90 degrees. So we have sine 0 degrees, right? Sine 0 0. So in this case, what is torque in this case? 0, or you get minimum torque, which means when you place this dipole moment, okay, when the dipole moment is aligned with the electric field over here, the electric dipole does not experience any torque. Okay, now this condition is called as stable equilibrium position. There is one more condition you can come across, that is, what if this dipole is completely rotated? Look at this difference. Earlier we know we actually saw in the previous case that this side over here it has positive charge, okay, this plate on the other side is negative charge, so the electric field line we have is from positive to negative charge. This is, we have created an external field line over here, right? Now same thing we are noticing, okay, now same field over here, right? So if you see the electric fields, if you see on one side, obviously let's say this is a positive plate over here and this is negative, so obviously electric field is from positive to negative charge, but look at how this charge is kept. Now this is a positive charge, so it will experience a repulsive force, right? It will experience a repulsive force in this direction, right? So this also will get because of the negative place, this negative charge will experience a repulsive force. In other words, this negative charge will be attracted towards this positive charge, and this positive charge will be attracted towards this negative plate over here, right? So this is the direction, and we know dipole moment is always from negative to positive. Now in this case, think about what is the direction of the electric field to the dipole moment. Electric field we know is in this direction over here, right? Electric field is in this direction over here, okay, and look at the direction of the dipole moment. Dipole moment is in the completely opposite direction, so here angle between them becomes 180 degrees. Alright, so here what we know, theta over here ends up becoming 180 degrees. Okay, so again if you see, we have to find just a second guys, really sorry, just a second. Right, so here we will end up finding what is basically, just a second guys, really sorry. Right, so again in this case we will end up finding what is the angle over here, okay, and we can see that we have an angle dependence of sine 180. So again we know torque is equal to PE, okay, sine 180 degrees. So sine 180 is 0, so torque is 0. Again in this case if you see, the turning effect this particular dipole experiences 0, but this is called as unstable equilibrium position. This position is extremely unstable. If you disturb this particular arrangement, what we see is that this particular dipole will actually rotate by around 180 degrees so that it can align to its stable equilibrium position. Alright, so this is all about when an electric dipole is placed in an external external electric field. Alright, now with this note we are coming towards the end of today's class. But let's see, like, there are lots of free classes happening on the Unacademy platform, and the description link is down below. So do subscribe to that channel as well. Alright, and again, if you like the video, please share it among your friends. Okay, subscribe to the channel and click on the bell icon, so before any class goes live, you can actually you will get the notification. Alright, so see you all in the next class. Bye.